Hi, and welcome to MSc. In this video, we're going to be looking at multiplying and dividing radicals. So the multiplication and division of radicals is performed in a similar manner to polynomials. So we're going to look at some examples of multiplying polynomials and then compare them to what we do with radicals. So let's look here. If I had this, what you would do is you'd multiply the 3 times the 2, which is 6, and the x squared remains unchanged. So you'd have 3 groups of 2x squareds, and so in total you'd have 6x squareds. So same thing happens here. I have 2 of the root 5s. If I multiply by 3, I'm going to get 6 of the root 5s. Notice that the 3 does not multiply the radicand of the radical. Just the coefficient multiplies. Very similar, or exactly the same really, to what you did with other algebraic terms that you've already encountered in mathematics. In this scenario, we would distribute this 3, and it would multiply both of the coefficients. And again, when there's no number there, the coefficient is 1. So this would be 6x squared, just like it was above, and then you'd have an additional 3x. And again, those cannot be added because they are not like terms. So let's look over here. We'd have the 3 times the 2, the 3 times this coefficient of 1 that we didn't write, and this would give me 6 root 5, just like it did above, plus 3 of the root 2's. Again, I cannot add those because root 5 and root 2 do not have the same radicands, nor can I simplify them. If you've not looked at my videos on simplifying radicals or on adding and subtracting radicals, I encourage you to go look at those and then come back to this video when you're done. Moving on with another example here. If I had 4x times 5x, well, in this case, I would multiply the 4 and the 5 together, and I'd get 20. And then I would multiply the x and the x together, and I'd get x squared. So this is exactly what we do over here with the radicals. I'm going to multiply the 4 and the 5, and that's going to give me 20. And then I'm going to multiply the root 5 times root 5, and that's going to give me square root of 25. Now, however, unlike the 20x squared, there's nothing more I can do. I can do more here. I always want to look at my radical and see, can it be simplified? Well, in fact, this one can be. And not just simplified, but root 25 is just 5. So I can say that this is 20 times 5, which is 100. So sometimes when we multiply and divide radicals, there's an extra step than what we'd have if we were just doing x's and y's and x squareds. So let's expand this further still. Let's look at this scenario. If I had different values here, how would that change things? Well, I know I multiply my 4 and 5 and my x and y. And so this will be 20 because of the 4 times 5, and then I just write x, y. And there's nothing more I can do in that example. Over here now, unlike having the same radicals, root 5 and root 5, I have different radicals. So that's fine. We're still going to multiply the coefficients together. 4 times 5 is 20. And then we're going to multiply the radicals together. And I'm going to show you that step here. This will be 5 times the 15, right? Which is going to be 20, and it's going to be root of 75. And again, I need to check to see if this can be simplified. Can I simplify this further? Well, I can. The root 75 can be broken down into 25 times 3. So root 25 times root 3, because 3 times 25 is 75. And root 25 we know is 5. So this would be 20 times 5 times root 3, which would equal 100 root 3. So again, with algebra, until I know what x and y, I can't do anything more. But here with radicals, I can multiply the radicals, look for ways to simplify the radical that's left by looking for perfect squares in the radicand and simplifying accordingly. Let's do a division example here. Now, so if I'm dividing here, we know we're going to divide the coefficients. So 28 divided by 4, that's going to be 7. And x cubed divided by x, if you remember your exponent laws, we're going to subtract exponents. So this will be 3 minus 1, which gives you x squared. And again, there's nothing more I can do in that example. But notice again, we divided the coefficients and we divided the variable piece. So when we divide radicals, it's going to be the same process. We're going to divide the coefficients, and then we're going to divide the radical. So 48 divided by 2 is square root of 24. And then we always look to see if we can simplify this piece at all. And we look here and, well, 24 is not a perfect square, but in there is 4. 4 is a factor, and 4 is a perfect square. So I could rewrite this as root 4, and 4 times 6 is 24. 4 is the perfect square, and we'd have it like this, which then would give me 14 root 6. So very similar with multiplying and dividing with what we've done previously in algebraic terms to what we now have with radicals. So let's take this one step further, look at some examples where we need to FOIL some things out and see what that would look like. So let's work through these. Here what we know, when we have situations like this, we're going to multiply the 2 by both terms, and then we're going to multiply the root 2 by both terms. So let's start this out. We're going to have 2 times 3, which is 6, and then we're going to have 2 times the negative 5 root 8. Don't forget that negative. And we know when we multiply, there's no radical piece, so all we're going to do is multiply this by the negative 5. So this is going to give me negative 10 root 8. Then we're going to have the root 2 times 3. Well, the 3 is just going to multiply the coefficient of 1 by 3. So this is going to be positive 3 root 2. And then we'll have this radical times this radical. So the root negative 5 sticks around. And then we'll have 8 times 2, which is root 16. Incidentally, you could have reduced this root 8 originally, and that wouldn't be a waste of time. But it's not a huge radical, so I'm not worried about reducing it too much in advance. And as it turns out, we're going to have to reduce it eventually anyways. But the numbers don't get so huge that there's a huge benefit in reducing early. So now I look at this, nothing I can just add, because these are all different radicals. They're all different terms. We can't just add unlike radicals. But I look at spots where I can reduce things. So root 6 minus 10, and then we can reduce this root 8, which we could have done originally, right? And we can say that that's actually root 4 root 2. Nothing I can do with this one, 3 root 2, although I notice the root 2's in common. That's going to be helpful. And root 16 is just 4, so that works out really nicely. I get rid of the radical entirely. So this is going to be 6 minus 10, and the square root of 4 is 2. Root 2 plus 3 root 2 minus 20. Well, now I see that the 6 and the negative 20 are like terms now, because they don't have any variable, nor do they have any radical components. So this is 6 minus 20, which is negative 14. This part here, I'll expand this for this example, although you can maybe see some spots where you can save some work by combining a few steps depending on your comfort level. The 10 times 2 is 20. Nothing to do here. And now I can see I have negative 20 root 2 plus another 3 root 2. So this is going to give me negative 17 root 2. And that's an exact answer, Nothing more I can do to simplify it unless I switch to a decimal, in which case it'll become a rounded value. Let's look at this, and this looks like a bit of a mess, but this also shows up in sneaky ways a little bit later in the grade 11 math. So let's take a look at what the answer is, and then it might become clear where it will show up later. So this one is going to be a bit of a beast because we have to times this x by all of the values over here, right? All 3 times. So let's do that first. So this is going to equal x times x is x squared. X times negative 3 is negative 3x. X times negative root 5 is negative root 5x. Make sure that that x doesn't look like it's under the radical symbol. Next, we're going to have the negative root 3 multiplied by x, by negative 3, and by the negative root 5. So negative 3 times x is going to give me negative 3x. Negative 3 times negative 3 is going to give me positive 9. And negative 3 times negative root 5, again, the 3 will just multiply with the coefficient of negative 1. So this will give me positive 3 root 5. Okay, that's 6 terms already. I have 3 more to go because this root 5 needs to then get multiplied all the way out. Okay, so let's do this part. So 5 times root 5, rather, times x, and then it's going to be root 5 times negative 3. So the negative 3 will multiply the coefficient of 1, so we'll get negative 3 root 5, and then the root 5 times negative root 5 will give me negative root 25. Okay, so we had a trinomial times a trinomial, and we got 9 terms. So let's go and try to add these. So let's look at the squared terms. There's no other squared terms, so it's just x squared. I look at my negative 3x. Well, I notice that I have another negative 3x here. So let's add those two together, and that's going to give me negative 6x. I also have these x terms, though. Negative root 5x and positive root 5x. Well, I could add those radicals, but one's positive, one's negative. Those terms actually cancel each other. So that was nice from this example. That's good. Now I'm on to my positive 9. I see no other whole number, although you might notice that the n number will eventually become a whole number once I simplify it. And then I have positive 3 root 5, which I can add to this one because they have same radicands, right, of 5. But one's positive 3 and one's negative 3, so those also cancel in this example. Well, that's also really, really useful. Okay, and then what I have left here at the end is negative root 25, which you might notice is just going to be negative 5 because the square root of 25 is just 5. And so this will simplify down to x squared minus 6x plus 4. And I can't simplify that anymore because of like terms, right? I can't do anything with the x squared and the x until I know a value to substitute in. And so we see situations like this when we're looking at quadratics, right? We see that this is a parabola. It's an x squared. So this, the 3 plus root 5 and the 3 minus root 5, those are going to be roots of this quadratic. And that's where we'll see this situation come up again as you explore further in to the mathematics. I hope you found this video helpful. Thank you so much for listening and watching. Please consider liking and subscribing. Thanks.